So we have proved the Pim's theorem. And now we want to prove what we want, the Menger theorem, the relationship between size of minimum separating set and then size of maximum independent paths. In order for that, since we want to prove it for various versions, we define the H parameter for these things. So we define kappa prime xy is the minimum number of edges whose deletion makes y unreachable from H, meaning that there are no edges from, no paths from X to Y. Recall that we are either in undirected graph or directed graph, or multi-graph or simple graph. It could be multi-directed graph, so there are four possibilities. And in either case, we define in this way, and let lambda prime xy as the maximum size of the pairwise edge disjoint xy passes. And as we want to prove, we don't want to repeat the same proof for, almost same proof for vertex version and edge version twice. We want to prove them in one go. The following concept will be useful for us in this purpose. We define something called line graph, which is the graph where every vertex is corresponds to the edges in the original graph. The line graph of, say, multigraph G, which is written, we write as L of G, is the graph whose vertices are the edges of G with two vertices of the line graph E and F are adjacent when EF are the edges of the original graph, which is vertices of the line graph, with EA is UB and F is DW. Okay. And also we can consider line diagram. Of a diagram is defined in the same way, with edges being ordered here, meaning that if E is an edge from U to B, and then F is an edge from B to W. So, for example, if we have a graph here, A, B, C, D, E, that's your edges. This is your G, then L of G is what? A, B, C, E, D. So this is the line graph. And for diagram, what? A, B, C, D, E. How does it? From you go from U to B and then B to W. So that means from here to here, A to C, A to D, A to C, A to D, but not A to B. A to B is not okay because B is going this way and then it's going this way. And here C to E, and this is the line diagram. Then, because we want to take the directed path, so we define it this way because we want to ensure that the directed path in the line graph also corresponds to the direct path in the original graph. So if we go in this way, then that corresponds to the directed path of length. That's what we put forward. That's why we define it this way. Now, what? The Menger proved what we want. Kappa xy equal lambda xy in 1927. And since that, I mean, there are other versions also proved. So this is the local version. And the global version this implies that round down like so. This. If you know this, then we can actually prove this. And also there is edge. So there is local version, global version, edge version, vertex version, directed version, undirected version. And there are two choices. So there are 8 combinations. And all of them are called just Menger theorem. So let's state it. If X, Y are vertices in say multigraph or diagram G, then what? Kappa xy is same as lambda xy when xy are not adjacent. And kappa prime xy and lambda prime xy are same always, even if they are adjacent. So how do we prove? Proof is as we mentioned before. So you take X and you take vertex Y and you take the capital X to be neighbor of Y, capital Y to be the neighbor of Y. Or, I mean, in directed case, you take the out neighbor, then you take the in neighbor. And we use KAIST theorem. Then we get this first part. Okay, I will not write it down. And then for the second statement, this H version, we take the line graph of G. And like X is the set of edges leaving X. The Y is the set of edges entering. Okay, we will write it answer instant. For undirected case, we just take directed incident with x and incident with y. And for directed case, the ones that leaves x, not the ones entering, and the ones that enters y. And apply pimps here. Then this Menger theorem is proved. Okay, and then using this, so this is the local version. Using this, we can characterize K-connected graph, which is also called Menger theorem. Yeah, I will now write down the, to prove it in which year. So for graph G, or graph G, but G is K-connected if only lambda xy is at least K between any two vertex x and y. You can find the independence passive, the K independent passive for all x, y, and two is K edge connected if only between two vertex x and y, you can find the edge disjoint passive, rational edge disjoint passive. We can find the at least K edge disjoint passive. So this is almost a corollary of the previous one, except that this one is for all. And before here, this equality is only for non-adjacent x1. So there are that's one point that we need to check. In order to deal with that, let's prove this lemma. Division of H, it reduces the connectivity by most one. We want to prove this. And if you take an H in there, then let's say this is the H that you want to disconnect. Then what? If the connectivity drops, then what happens? There must be a vertex there. S will size and most the connectivity of G minus 1 such that G minus xy minus S is disconnected. But what do we know? If S had a size smaller than the connectivity of G minus S is connected. That means xy is the only edge of the edge cut from say some set X to some set Y in G minus S, with X being in its capital S and Y being in this set Y. So you have X and Y is S, X, and Y. What do you want to do? So we have this S, and then we wanted to, instead of deleting this edge, we could delete the vertex to play the role of deleting this X, then this becomes separating that, or this becomes separating that, when there is additional vertex here. So if this is just X itself, then taking this does not give you disconnect itself. So if X has side at least 2 or Y has side at least 2, then either S union with X or S union with Y separates G. That means, so this S has size at least the connectivity minus 1. So this is what we want. The connectivity drops by -1. Otherwise, what? Otherwise, if S has size, the number of vertices is -2. But what do you know? But by definition, connectivity is at most number of vertices is -1 at both, which is S plus 1. So S is again at least the connectivity minus. So in any case, we have this inequality. With this lemma, now we can prove this theorem. So what do we know? The connectivity, the edge connectivity is easier case, so let's clear it. So this is the minimum of the all local, separation between any two vertices. So the previous one implies this. We only have to be careful on the vertex one, because the previous one consider all the pairs which are not adjacent. The adjacent pairs are not considered. First, let's show this one. If this is for all pairs, then what? Previous Menger theorem. Is that kappa xy equal lambda xy or xy not in there. So what? Activity is minimum out of all xy not adjacent kappa xy. That because of this, and because of this assumption, we have that it is K-part. And the other direction. The other direction is we assume that it is K-connective. And by the previous Menger theorem, we only need to show that the assuming K connectivity, I mean the for adjacent pair, the number of independent passes between them is at least the connectivity. But what we know is XY edge itself forms an XY path, and it lies in no other XY passes. What do we know? In G, the lambda between X and Y, the number of independent passes between X and Y is 1 plus the number of passes between X and Y after deleting XY. You delete the edges from X and Y. If there are 3 independent passes, this is 3, then this is 4. You just add this one. This one is like joker, so you can always add. And what do you know? In this graph, in the previous Menger theorem, they are not adjacent, so it's same as kappa. And in here, by the definition of connectivity, it's at least 1 plus connectivity of G minus X1. And in the lemma, we show that this is at least connectivity minus 1, connectivity of the ordinary black minus 1, so this inequality holds. So this inequality holds, so this direction is proved. We proved the Menger theorem. And when we apply Menger theorem, so oftentimes we find the path between X and Y. And oftentimes we find the passes between Z to Z and Z. We show the XY link that we take before. But oftentimes there is also a case that between one vertex and then Z, we want to find the passes which are independent but which are sharing only the starting vertex. So we want to give name on such a concept. So for a vertex X and a vertex set U, we define on X cube band. So you take one vertex and then passes. It looks like a band. I mean, yeah. So we say that this is the X cube band of size K. It is a set of K passes from X in U that pairwise share only X and HU only at their endpoints. Then we call it a band. So the second meaning that we don't allow passes that visit once and then twice. So those are not what we want. And we prove this lemma. For the band lemma. No. A graph with more than k vertices is k connected if and only if it has an axial band of size k for each. Sorry, so x and u with u having size k, this k, then x is a vertex not in. So whenever you have a k-connected graph with more than k vertices, and you can freely find the x u band of any choice of vertex and then any choice of set of size u. You want to prove this. In order to prove this, let's mention this simple lemma called the expansion lemma. And if G is a k-connected graph, and G prime is formed from G by adding a vertex U. So at U vertex with at least k neighbors of G, then this graph G prime is still k connected. This is pretty basic lemma. And using the definition of the connectivity, it's not difficult to actually verify. So we will omit the proof. Then we use this to prove random. So, but let's use this direction. If it's a k-connected graph with more than k vertex, and how can you find it? You have a graph G, and you have U. You have this k. And what you do is you add a new vertex, then you make it adjacent to all U. And this U graph is G prime. And G prime is k connected. So you have X here. So you use Menger's theorem. And what? In this G prime, you find the k independent passes between X and Y. But Y is only adjacent to U. So all of these passes, if you just cut out the Y part, then it stops at this U. Everything more vertices here, but then this provides a XU band of size k. So yeah, I will not write it down, but that's the proof. And then the other direction, what? If C is the other direction, you take the contrapositive. If C is not k connected, and what happens? Then we can take as the separating set. Separating set of size k minus 1 as E has more than k vertices. If she has exactly k vertex, then yeah, there are no separating set of size k minus 1. But here we assume that she has more than k vertices. We choose X and Y in distinct component of T minus S, and let U be S union with Y. then what do we know? So contrapositive is that we want to show that if it's not K-connected, there are certain choices of action U such that the fan does not receive. And this is the choice. So you take U and then the what? There is no XU fan of side K since every XY path intersects X. So this proves the other direction. So we prove this band lemma, which we'll see that it's handy in some cases. So what have we proved? We proved this Menger theorem, which shows that the separation property and the binding many independent paths between two vertices are closely related. The size of minimum separating set and then the size of the maximum fraction of maximum fraction of independent set, independent paths between them have the same size. As the connectivity is defined using the separation property, and this equality allows us to freely convert the property of K-connectedness into finding many independent paths. That's often used. So that's what we did today. And then next time we will consider some statement about cycles. So connectivity, as we have seen before, connectivity and cycle are closely related. The codices are the ones that doesn't belong to any cycle. Then we use cycles to characterize the trees and to connect the graph. Technically we use this year decomposition, but which has intuitively similar to cycles. We are attaching paths and paths, which gives us the partial cycle, if you want to think it that way. So there are indeed some close relationship between connectivity and cycle, and then we will consider them in the next video. Okay, thank you for listening. See you later.